All right, so we're on to example 12.4. Clearly, this is a different setup. Previously, we had the Y to Y connection. This is a delta to delta connection. You can see our source is delta connected and our load is also delta connected. And so this has some implications, but they're giving us the load impedance here, 20 minus J15. So that means that Z delta for each one of these is 20 minus J15 ohms, okay, for all three loads, and they're not giving us any line impedance. So again, we talked last time about how there was an impedance in these actual transmission lines, but they're assuming that those transmission lines are ideal in this problem. So all we have to worry about is the loads, which is great. First of all, they give us the load impedance, which I just talked about. Second of all, they give us the fact that, let me highlight this. This is a positive sequence generator, which I talked about previously here. As they say, positive sequence is assumed, or an ABC sequence. For a positive sequence, that just assumes that VAB, in this case, they're giving us VAB. I don't like drawing it with the plus. With the plus and the minus, I like drawing it sinusoidal. We can put our plus and minus here if we want. That's going to be VAB is equal to, for them, they gave us 330 angle 0. We have to take into account the positive sequence, which means that VBC is equal to 330 degrees minus 120, or 330 volts minus 120 degrees. If it was the negative sequence, VBC would be the plus 120 signal, and VCA would be the opposite. But this is what the positive sequence means. It's just telling us how. It's really just a notational thing so that they don't have to write all these voltages on the schematic. That's the only reason why they tell you something like the positive sequence. When I give you an example, I'll just write these voltages out, or a problem on a homework or on an exam, I'm going to give you these voltages written out. I don't think it's necessary to memorize the positive sequence. There's no need to confuse people. So we can just write them out, and I will write them out, but just because I'm solving book problems right now, we're going to have to deal with their lingo. But really, this is all that it means by the positive sequence. It's just telling us when we go from A, B to B, C, are we going down 120 degrees or are we going plus 120 degrees? And it does make a difference with the calculations, but really it doesn't matter. Okay, so it's asking us, let's grab my highlighter again. What is it asking us for? It's asking us to calculate the phase currents of the load and the line currents, right? So we need to find two different things here. We need to find, let me grab my red. We need to find the line currents and the phase currents. So 6 different currents here. And so if you remember from when I talked about the delta to delta sequence here, we can see pretty clearly that the VAB gets placed directly across this Z delta here, and that creates a circuit, right? So I know the voltage across this Z delta is just VAB, right? So I could pretty easily find IAB by just saying VAB over Z delta. So let's go ahead and do that. I'm going to say IAB is equal to VAB, right, divided by Z delta, which is, let me also shrink these. This is taking up a lot of space here, which is, and again, that's the reason why they don't do this. But that's my positive sequence. So just so that we have that in mind, I can rewrite this. We know VAB is 330 volts. Sorry, 330 angle 0 degrees volts. Z delta, let's just go right ahead and find the phasor for that right now so that we can just have it. I'll go 20 minus 15i, and then I'll go math. Okay, so I get that Z delta, the phasor form of Z delta, is 25 angle negative 36.87 degrees ohms. Okay, so we can throw that in for our phase here, 25 angle negative 36.87 degrees ohms, and I can find IAB by taking 330 divided by 25, which gives me 13.2. And then my angle is going to be 0 minus negative 36.87, or a positive 36.87 degrees amps. Okay, so that is IAB right there. I'll make a little bit bigger of a box there. That's my IAB. That's this current. That's this current here. Right, so well, how would we find IBC and ICA? Well, we can do a couple of different things. One, we can look at the table, right? We could come back to this table and note that for a delta to delta system, IAB is VAB over Z delta, IBC is VBC over Z delta, and ICA is VCA over Z delta, right? And I guess that's pretty much the same as what we did here. My assumption is that they're just going to be another 120 degrees phase shifted. But let's go back and just do the math for that. And then in the next video, we'll go ahead and find the line currents, since this is just going to be the phase currents. But this should be pretty straightforward, right? We found IAB. We should be able to find that IBC is just going to be 330 degrees angle minus 120 volts. Oh, sorry, I don't know why I keep saying 330 degrees. I think because it's so similar to 360, I'm just used to saying it degrees there. But it's volts, 330 angle minus 120 volts divided by my impedance, which of course we're going to see is going to give us the same amplitude, right? IBC is again going to be 13.2, but this time my angle is going to be negative 120 plus 36.87, so I can just basically say negative 120 plus 36.87, and I get negative 83.13 degrees amps. And of course, ICA is going to be 330 angle plus 120 divided by the impedance, and that is going to come out to 156.87, so 13.2 angle 156.87 degrees amps. And so I have my phase currents now, which is part of what I needed, right? I basically did the phase currents. And now in the next video, I need to find the line currents, and I'll be done with this problem, okay? So how we're going to find the line currents? Well, clearly we know this IA, it comes into this node and it splits between these two currents. So we're going to write a KCL loop at these nodes, and we'll go ahead and find our line currents using KCL, okay? So I'm going to end this video right here. In the next video, we'll go ahead and do that.